Now, what we proved for the partial sum of the Fourier-Haar series of a function from L1 is true also for the case where n is not necessarily the kth power of 2, but it's just any index. So the theorem takes the following form. Where this lambda and j, or let's put it in this form, lambda and I, yes, and I changes from 1 to n, those are the constancy interval for the first n Haar functions. And we know that they are mutually disjoint, their union is the interval 0, 1, and that their number is exactly n. We have n Haar functions, and the number of their constancy intervals is n as well. And this n, as I mentioned it already, is not necessarily 2 to k, it's any n. So, and which is very important, this lambda and j here is the unique constancy interval which contains x. So let's prove this general version as well. So first, introduce the function mn. Now we indice it by the same n. We did mk before, and now just mn. This is 1 over the length of the jth constancy interval, integral over the jth constancy interval ft dt. From its form, once again, it's obvious that it is constant on each of the constancy intervals, and of course the first n Haar functions are constant on their constancy intervals. Therefore, mn fx is the linear combination of the first n Haar functions. Let this be star and let this be 2 star. These two forms for mn fx. Now, to prove the theorem, we need just to see that this aj is equal to cjf. We will do this in 2 steps. So we want to see that aj is equal to cjf. First, we will see that aj is cjmn. Next, that cjmn is cjf. Cjmn is integral from 0, 1 mn fx chi j x dx. We replace mn fx by its expression as the linear combination of the Haar functions. So integral from 0, 1 sum. J is already used, therefore we will use the index small n, changes from 1 to n here, and a n chi n x, but we also have chi jx here, chi jx dx. Now sum comes in front, a n comes out of the integral because it does not depend on x. And we are left with this integral, which is 0 when n is not j and is 1 when n is equal to j. So n equals to j, n equals to j. This means we have 1 here, and the value for this expression is exactly aj. So this first thing is done. Now let's see that this holds as well. we don't need this derivation anymore. Cj mn is integral from 0, 1 mn fx chi j x dx. This integral we will introduce as a sum, a sum of integrals over the constancy intervals. J is used, so small n changes from 1 to capital N, and then here integral lambda n in the small nth constancy interval, and then we have mn fx chi j x dx. Now we notice that this chi j, okay, we recall that this chi j is constant on each of its on each of these constancy intervals and takes value rj on each of them. Therefore, it should be taken out of the integral rj here, integral lambda n and then mn fx and then dx. Next, sum n changes from 1 to n, this constant value rj, and here ex is the integration variable, as we noticed before in the first part of this discussion, and therefore we, in the expression of mn, the expression star, this lambda nj appears as lambda nn, because in this expression, in expression star, lambda nj is the unit constancy interval which contains this x. Therefore, this x is in lambda nn, and the expression for mn is this one when we have lambda n, small n, in the place of this lambda nj. So let's have this here, lambda n 1 over the length of lambda n times integral over lambda n f t dt as well as dx. Then let's erase these expressions both. Here, sum n changes from 1 to n rj integral lambda n ft dt, and rj goes inside the integral, taking the form of chi j at t dt. Finally, this is integral 0 1 ft chi j t dt, and this is exactly cj at f. Therefore, this version, general version of the theorem, holds as well.